Welcome to Spring LIB.
Here we're going to look at a capacitor plate arrangement that initially has no dielectric in it, and then we are going to disconnect the battery, which is initially set at 120 volts, and we are going to place a dielectric between the two plates, separated with gaps, equal gaps on either side, each of 4 millimeters. So this is a nice symmetric arrangement. And we're going to ask, how does this change the capacitance? So there are a couple things to realize is that there are two ways that you can actually set up this dielectric. One of which is to leave the battery connected. And if you put the slab in between, more charge will dance onto the plates due to the bound charge inside the dielectric. So let's make the positive plate above and the negative plate below. What will happen is if you've disconnected the battery, the charge remains the same. There's no place for it to go. It's going to stick on those plates, and that's the second way you can set up this arrangement. But in either case, the capacitance is going to change because of the bound charge that builds up on that dielectric. So it actually has an electric field inside of it that propels charges to go to the surface. So that's called bound charge. And for a uniform electric field that occurs in the plates, that bound charge occurs at the surface. There are bound charges inside, but they cancel each other. So what we're going to have to find is the new capacitance of this arrangement, and we're going to have to find the new potential energy stored. So we're going to start with our initial condition and look at some capacitor relationships. We know that the capacitance is equal to the area times the permittivity of free space over the separation. So that is a geometric calculation that we can do. And we want to use the permittivity of free space in there, a well-known constant. And the spacing is 12 millimeters or 1.2 centimeters, but we want that in meters. And that works out to be in the picofaraday range. I will write the picofaraday out as 88.5 times 10 to the minus 12. In terms of the potential and the electric field, though, we know that capacitance is defined to be the ratio between the charge on the plates divided by potential difference. So C equals Q over delta V. We can now find the Q that's on the plates. And this is a fixed quantity. I will point that out as we go along. And we won't forget our pico, and that turns out to be in the nanocoulomb range. I will write out the nano as 10 to the minus 9 coulombs, but the thing to realize is that does not change between the inserting of the slab and the initial condition. And the reason for that is the battery is not hooked up. If it were left hooked up, then you could have the capacitance change by having the charge change. So what's going to change is the potential difference across the plates. And let me just remind us of that. Q remains the same. and it's the delta V will change to make the capacitance bigger. And essentially the capacitance is bigger because of those stored bound charges in your dielectric slab. Okay, now to work out the new capacitance, so this is all initial stuff. To work out the final situation, I like to use something called the D field. The D field stands for displacement, and how it differs from the electric field is it depends just on what's called the free charge. So there's a distinction between free charge that is not bound inside an insulator, and in this case on the conducting plates, meaning that it's free to move around. It doesn't have to be on a conductor. It could be floating around as a point charge in space, but usually with parallel plates, that free charge is sitting on your conductor plates. And the displacement field depends only on that, and it is related to the electric field through the dielectric medium. The dielectric constant times epsilon naught times E is equal to D. So remember that the free charge is fixed, and we can find the D field fairly readily through equation 1, which is D equals Q over A. And then we can find the electric field in our three regions. The gap, we'll call that G for gap, and D for dielectric. We'll call it die and gap. There are two gaps, so once we find the electric field in one of those, we know the electric field in the other. Okay, so the electric field in the gap is equal to the D field over epsilon naught, or Q over A times epsilon naught. And we know the charge now. Remember, that's not changing. And we know the area, and of course we know epsilon naught. I won't write it in. It's a permittivity of free space. And when you calculate that, you get the electric field in the gap. And we could have done this before we stuck the insulator in there. That is, it was a gap before, and so that electric field is not changing. And those are in both the gaps, and we can figure out the potential difference across each of the gap. Remember, potential difference is the electric field times the spacing between the plates. In this case, we're calling that little delta. And we get delta is 4 millimeters. So the potential difference in the gap is 40 volts. We could have figured that out because it was 120 volts with a third of the gap filled, with all of the gap there. So with a third of it left, we get a third of 120. Meanwhile, in the dielectric, that's the D field, the Q over A, and then kappa epsilon naught in the denominator. So that is going to get reduced. This is the action of an insulator, is to reduce the electric field inside of it. In other words, those bound charges kind of act as a shield against the electric field. And we can figure out then the potential difference is the 2.08 times 10 to the third volts per meter times the 4 millimeter spacing. And then we get 8.3 volts. Okay, so now we know in this new situation, I'll just redraw it very roughly, our dielectric. We know that we have the 10.62 nanocoulombs on the plates, plus or minus. Okay, letting me write up there. And we know there's 40 volts each potential difference in the gaps and 8.3 volts across the insulator. So we now know that the total potential difference is 88.3 volts, more or less. Could be an error in the last sig fig. So we can now calculate the new capacitance. It's still Q per delta V. And notice with the voltage going down, we now have a higher capacitance, which is the action of the dielectric. And that turns out to be 120 picofarads for the new capacitance. So yes, it went up noticeably by the addition of the dielectric. And our last goal is to use potential energy stored in the field to figure out the amount of work done to insert the dielectric. And let's just take a gander before we do the calculation. Do you think it'll take positive or negative work? I would guess negative work because that dielectric will get charges opposite those on the plate. And so it should be actually kind of drawn into the field. The field will not try to repel it. It'll be kind of helped along by the electric field in between those capacitors. So I would guess that it takes negative work physically. But let's find that out. So the work energy theorem says the work done by an external agent is the change in kinetic energy. We don't have any of that, nothing zipping around, plus the change in potential energy, which we do have. The potential energy in a capacitor is 1/2 C delta V squared, and we simply have to find the final amount minus the initial amount. And we can do that using the final capacitance, 120 picofarads, and the final voltage, which was 88.3 volts. Units of joules, and the initial amount is 1/2 times the initial capacitance, 88.5 picofarads, and 120 volts squared. Working that out, that turns out to be, find a place to write here. Okay, so we'll just go ahead and calculate those out. 1/2 times 9.4 times 10 to the minus 7 minus 1.27 times 10 to the minus 6 in joules. Yes, and it does turn out to be a negative quantity, a not very large negative quantity. So you may not even feel this if you were the one inserting the dielectric.